Thank you. I would like to start by acknowledging the organizers for putting up this wonderful session. I have been so much inspired by all of you. So we started the day by looking at the epoch where we are from the geological position. I would like to close the day by looking at it from the perspective of a theoretical physicist in terms of materials. So I do theory, but all the three images you are seeing there are experimental images. So the ages of humanity have been named depending on the kind of materials which were available for building tools. And so we went from the Stone Age to the Bronze Age to the Iron Age, and we are now at the Silicon Age, closing it. So actually, the fundamental physics for the Silicon Age was established long ago. We had the Nobel Prize for the transistors in the 50s, 1950. And this is all based on the semiconductors, like silicon. And a semiconductor is nothing but a material that interpolates between a metal, like copper, and an insulator, like plastic. So in metals, electrons are running, and the motion of electrons could be associated to the number 1. And in insulators, they are not running. This is a 0. So by writing series of 1s and 0s and reading them, we have all the technological devices that we use on our daily life, computers and telephones and everything. But there is a problem, and we were just talking about the cooling. It's the energy that's lost, because when the electrons are going through the silicon, and even if silicon is very pure and perfect, the electrons will meet impurities, they will meet defects. And when this happens, they scatter, and they lose energy, and they lose a lot of energy, and our devices get hot. So, from the materials perspective, this is a huge loss. Could we do something to overcome that? Okay, that's my perspective today. The problem is with all that, we are burning our planet. And Pope Francis has been telling us we should change our behavior, we should change our way of handling all that. And I completely agree with him. I find it very curious that all of our students are vegans. They are ready to stop eating meat to make our world better. But they keep sending messages and videos, and they don't even realize how much energy this costs. And nobody's telling them this costs a lot of energy. So education is very important. But there is another thing that we can maybe do, and me as a theoretical physicist, I want to look at my research with some perspective to help solving this problem. So could we find materials that can do the same as silicon is doing without losing energy? So yes, maybe we can. And everything started with our chair in 1980. So Klaus von Klitzing has discovered a new state of matter by having 2 types of semiconductors like silicon, and looking at the interface with a very strong magnetic field, he found a material that it's at the same time insulating, like plastics, and metallic, like copper, but better. So this material is insulating in the bulk and has these currents running only at the edges. But these currents are quantum, they are protected. They are protected by the topology of the material. They don't lose energy. If there are defects, and these defects do not break the protecting symmetries, they ignore them. Okay, so this is a wonderful discovery. And there has been another beautiful discovery in 2005, which was graphene by André Geim and Kostya Novoselov, which is a very thin material, 1 atom thick layer of carbon. So how are these 2 things together going to help us to maybe improve on the energy problem? Well, the effect which was discovered by Klaus von Klitzing has already served for many purposes, like the issues of the standard of measurement. But if we want to bring this into devices that we carry into our pockets, we need to improve. Because to get these effects where these electrons, and you see what is running at the boundaries of the material, are like these magnets pointing up and down. These are the electrons in these protected currents that don't lose energy. But to get into this state, we needed to go to very low temperatures and apply very strong magnetic fields that I cannot put in my pocket. However, a few years later, in 2005, Kane and Millet got the breakthrough prize because they proposed that it's possible to have this effect as an intrinsic property of the material. You don't need a magnetic field. If you have a material which has what is called a spin-orbit coupling, so the direction that the electrons are moving couples with its orbit, then we don't need a magnetic field. And we are not having a charge current, but we have a spin current, which means the electrons rotating clockwise go to one corner, they're counterclockwise to the other. But it was beautiful. We still have a problem of a low magnetic field. The original proposal was for graphene. It didn't apply, but right after Shusheng Shang's group proposed another type of material, also a semiconductor quantum well, mercury cadmium telluride, and Molenkamp did the experiments, and indeed, he could see this beautiful effect of these protected currents that don't lose energy, but at very low temperatures. So can't go to our pockets yet. At the same time, in 2007, André Geim and Kostya Novoselov now, they measured the same effect that Klaus had measured in 1980, but now in graphene. And guess what? We could see these beautiful quantum effects at room temperature. That looks very promising. But still, we needed a 29 Tesla magnetic field, not for my pocket yet. But in 2017, we finally got there. So, by taking a material that is as thin as graphene, but instead of being made of carbon, it's made of bismuth. It's called bismuthine. Now, we could have these effects without any magnetic field. It's intrinsic and at room temperature. So it looks extremely promising. We have dissipationless currents that could be used for normal computers, for storing data. But these currents are only at the boundary. So I have a big sample. All inside is like an insulator, and the currents that I want to use are just at the boundary. So you would say, we need more boundaries, right? How to get many boundaries? Well, there is a way. Fractals. Fractals are these beautiful structures that have self-similarity. I keep zooming in on them, and I always see the same. And if we take a very simple fractal, which is called a Sierpinski triangle, you start from a triangle. It's a two-dimensional object. Choose each middle point from each side, build an inverted triangle, and cut it out. You remain with the three smaller triangles, cut out another inverted triangle in the center of each one, and go on ad infinitum. You will end up with a structure which is no longer two-dimensional, as you started with, but it is also not one-dimensional like a line. It has a fractional dimension, 1.58, and lots of boundaries. So it looks very nice. But then you can already think what was said today, how to merge high-tech with low-tech. They are really in nature everywhere. Nature has been using fractals to build the branches of the trees, the roots of the trees, the leaves. Our body is profoundly fractal. Circulatory system, the lungs, the intestines, the neuronal system, even the heartbeat is fractal. And these fractals are also very important in technology. If I do an antenna with a fractal, I have large and small frequencies that I can send and receive simultaneously. They are very useful to build solar cells. And they are very beautiful. They appear to our eyes as beautiful because they are in nature. So we would like to use these fractals because I have lots of edges that I could use as dissipationless currents. But the first question we would ask is, if I put electrons in a structure like this, do the electrons perceive that they are in a fractal? Can they see that they are living in dimension 1.58? So we went on to answer this question, and for this we use this technique of quantum simulators that you heard today from Emmanuel Bloch, but we did quantum simulators with electrons. So in 1993, the group of Don Eigler has built what is called a quantum coral. So each of these spikes that you see in this circle is one atom of iron. And he built them on a nanometer scale. The separation between two of them is 1 nanometer. And what you are seeing inside are the wave functions of the electrons. So you heard today that the electron is a particle, but also a wave. And there you can see the waves, like the corals that are forming waves in the sea. And it took about 20 years until people started combining all these quantum corals to make a lattice. That was the work of Hari Manoharan. And that movie you are seeing was made by IBM. It's A Boy and His Atom. It's the smallest movie ever made. Each pixel is one atom. So we use this technique to build fractals, but just up to the third generation, because in physics, these fractals are not going to infinity. They are finite. So what you are seeing on the right is an experimental image. You take a surface of a metal with a flow of electrons, and you put little mountains. Each of these black dots you are seeing is carbon monoxide, and the electrons will distribute in between, and they will form a fractal. And then you measure the wave function, the modulus of the wave function square of these electrons. And you ask yourself, can they perceive the fractal dimension? And the answer was yes, we could prove that. So we were very happy when Nature Physics selected our work as one of the 15 highlights from the last 15 years. And it's then the birth of a quantum fractal. So we are bringing nature to the quantum realm. And now it comes the next question. Can I build these topological states, these current carrying states which do not lose energy in these fractals? So the classification, there is a kind of a periodic table for topological systems, as we have in chemistry. You look at the symmetries of your solids, and you look at the dimensionality, if it's a wire in one dimension or a plane in 2 dimensions, and you can immediately say it's topological or it's not. But now I want to go in between the dimensions. Is it possible? Thank you. Is it possible at all to have that? Well, in China, the group of Jingfeng Jia, he had a student called Shen Liu, and she started growing bismuth on indium antimonide and playing with the growth conditions, temperature and time, and so on. And then they observed that fractals were emerging in these materials. These are very small fractals, okay? And at that time, in 2021, they thought they are not topological. And took us 2 years to prove that indeed, yes, they are topological. So here you can see a picture. On top you see the structure, and in the middle bottom you see the substrate is insulating. There is a 0 there, and then you see a cyan spike. This is a corner mode at the structure that is there on the top. So they are topological. And we did lots of calculations. These are my 2 students who worked on this project. And we could show that indeed, you see, in pink and blue, pink means you have lots of electrons, and cyan means no electrons. It's their wave function, which is being imaged. And on the top right, you see two corner states. This could maybe be used as qubits. And then at the bottom left, you see an upper-looking triangle. The next one is a down-looking triangle. These are these marvelous states which could lose no energy, which are sitting at the boundaries, at the outer boundary and at the lower boundary. And we have been considering defects, all kinds of defects, and we could finally get a quantitative agreement between theory and experiments and understand why you have only two of these corner states, these two blobs there, instead of three, and why the upper two are stronger than the others. So we are understanding these materials. And now it is opening the path to go from silicon, which has lots of losses in energy, to maybe novel materials like bismuthine, which could have no energy loss. It is opening the path to create structures at non-integer dimensions, which haven't been explored in the quantum realm at all. It is inspired by nature and by the human body. It is a point where high-tech meets low-tech. And maybe we are making our first steps towards the quantum age, where we are going to have materials which are engineered according to the required functionalities and use quantum effects to avoid energy losses. So with that, I give you some of our references, and I think we are approaching the dream of producing currents without energy losses. And I thank you very much for your attention, and I offer you some fractal flowers.